moderate to high clay fraction. They will have quite significant clay content in them. And they are also CH type. Here also, if EB2 and 5, if any one of these three criteria is fulfilled, then that. And why do we need ground improvement in soft soil? There are two reasons. Number one, let us say this is my ground level, and this subsoil is soft. If I construct embankment here, number one, the soft soil, its shear strength is very low, or bearing strength is very, very low. And if you construct embankment, because of load of this embankment, there will be failures, base failure. Your base, including base of embankment and this portion, it will slide, and normally you will find a heaving at the after the point where your slip circle strikes the ground level. So this is one reason. Because of poor shear strength, there are chances of base failure. That is number one. Number two, what will happen is under this embankment load, this subsoil will settle, and eventually your embankment will settle. And therefore, if you put embankment here, after some time it will come here, it will come here. This settlement is quite significant. We will calculate also an example tomorrow and see. It is quite significant. And your all rail level calculation, formula level, formation level calculation, everything will go haywire. Finally, you will not be meeting the required level. So because of these two reasons, number one, so that there is no failure, no shear failure because of low shear strength, and to control to control the settlement of the embankment. One is embankment settlement. Second thing, time for settlement. This settlement continues in case of, let us say, this weak soil is 15-20 meter deep. Then it may continue up to 3, 4, 5 years also. And we cannot wait up to 5 years to start construction of track over the embankment. Therefore, for reducing the settlement as well as time for the settlement. To eliminate these two things, we need to do ground improvement and then only construct our embankment so that we can construct track quickly over that and the bank is safe also. So therefore, we have to do ground improvement number one for reducing consolidation time and settlement. The settlement we call consolidation settlement. We'll see it. What is it? And to increase bearing capacity or shear strength of the subsoil so that there is no base failure after construction of embankment. Now, if you see soft soil anywhere, it has got some very, very typical properties which you will find always associated with soft soil. Number one, they have got very, very high amount of percentage fines. That is, soil passing 75 micron sieve, it will mostly be more than 50%. Your percentage fines will be 50%. It goes up to 70%, 80% also. 50% certainly, otherwise it is quite high. They will have very high liquid limit, more than 50%, and equally high plastic limit also, and therefore very high IP also, plasticity index. Liquid limit certainly is more than 50%. I have seen up to 70%, 80% also. That high liquid limit. They have tendency to retain a lot of moisture. Means once they get saturated due to rain or due to any other water, their drying takes a lot of time. Very low permeability type of soil they are. So evaporation of water is very, very less, and their natural moisture content also is normally very high. Low permeability, very low permeability. That's the reason that evaporation of water takes time and they tend to retain water for a long time. And their shear strength is low. All these soft soils, we have seen 100 shear strength less than 25 kilopascal and value and all. So shear strength of these soils is very low, and it varies with depth. Shear strength changes with depth. Normally, as you go down, except in few exceptional cases like laterite soil and all for top portion. Otherwise, normally as you go down, as you go with depth, it increases. Your soil improves and improves and improves as you go down. And if your underlying shear strength of soil is even less than 12 kilopascal also, then we call them very soft soil. Even in soft soil also, soft soil is 25. So below 25, we call them soft soil. But if it is less than 12 also, then they are known as very, very or very soft soils. And these soils, their compressibility is very high. It means the settlement on application of load is very high in these soils. And if you have organic content in it, it increases the compressibility characteristics further. More is the organic content, more will be the compressibility. It will further increase. Even without organic content also, they are highly compressible type of soils. Now, we will see something about consolidation. What exactly is consolidation? And now, whenever you apply any external load to saturated soil, as we have seen previously also, our soil mass consists of grains. Then we have water molecules. So some water is around them, mostly it is around grains. There may be some water molecule between these pores also, and then we have air. Now, when you apply any load, any external load, now in normal case, this soil is under equilibrium. It means this water is at atmospheric pressure and there is an equilibrium. Now, if I apply any load, it may be due to construction of embankment or due to whatever reason. Because of this load, other day when we talked about effective stress and total stress, there will be some stress on these soil particles, grains, and this water will also develop some pressure, and that pressure we call as pore water pressure. So this water goes under pressure. So when external load is applied, the load is transferred to soil particles and the pore water. This leads to development of pore water pressure. And since it is under pressure, and whereas outside here, this excess pore water pressure is 0, it means it is at atmospheric pressure. So naturally, there will be a tendency for this water to squeeze out from point of high pressure to low pressure. So this pore water pressure tries to squeeze out. With this squeezing out, your pore water pressure will reduce. So moving out of this reduces the excess pore water pressure, and your volume of soil will decrease because water is coming out. So there will be settlement or in decrease in volume. So it causes reduction in volume of mass, that is settlement, and this process is known as consolidation. If you remember, we had first compaction, where air goes out, and in consolidation, your water goes out. And this consolidation continues till this pore water pressure goes from U to 0, means again it becomes equal to atmospheric pressure. Again equilibrium is established. So till this action take place, means your pore water pressure starting from U, it comes back to 0. Till that happens, your squeezing out of water will continue and settlement will continue. Now, at what rate this will happen depends on so many parameters. Number one, how much this water molecule has to travel to go out to get expelled. How much is permeability, because if permeability is less, this travel will take more time. What is the depth of this layer? How much is excess pressure? All these things, they decide this time of consolidation. But it is a very, very long time for clay type of soil or weak soils where you have got low permeability. If you have got weak soil of maybe 5 or 10 meter depth, then it may take years, 2 years, 3 years, 5 years, depending on all the factors. So this consolidation time can be a very, very long time. It is not a small time. So in case of porous, grained or cohesionless soils, this consolidation happens along with compaction itself. In case of granular soil or cohesionless soil, compaction and consolidation are almost simultaneously. The water as well as air pressure both will go out. There will not be any separate consolidation process from compaction. But in fine-grained cohesive soils with low permeability, as I told you, it continues for a very long time, which can be in years. And this rate of consolidation depends on the permeability of the soil, because that will decide at what rate water will get expelled out, magnitude of the load, and the depth of the layer to be consolidated, because that will decide the travel distance of your water molecule. So this is what is the process of consolidation in case of soft soils. Now, we have seen this equation previously also. The shear strength of soil, tau, or tau at failure, is given by this C plus sigma 10 phi. C is your cohesion, sigma is normal stress, and phi is angle of internal friction. We have seen this when we were talking about slow stability, that itself. When we talk about total stress principle, when we are not taking into account pore water pressure. But whenever there is pore water pressure, your shear failure is governed by effective stress and not by total stress. As I told you, this is Terzaghiy's theory. And then the equation is shear stress at failure equal to C dash. C dash is effective cohesion intercept. Then normal stress minus U. U is pore water pressure, and 10 phi dash. Phi dash is effective angle of friction. Now you see here, immediately after application of load, your U is maximum. Since U is maximum, your shear strength is minimum. And since shear strength is minimum, your factor of safety is minimum. As consolidation takes place, U value reduces from U to 0. It means this value goes down. Since this value goes down, shear strength goes up. And since shear strength goes up, factor of safety goes up. Therefore, as I told you previously also and now also, in case of construction of U embankment on soft soils, the most critical stage is immediately after construction, what is known as end of construction stage. Immediately after construction is over, that is the time when your U is maximum, and that is the time when your factor of safety is minimum. As your U goes down with consolidation, your factor of safety will improve. This is what is the basic principle which we must remember while working with soft soils. That my most critical stage is end of construction stage. Now, for consolidation, we need various parameters, so we do consolidation test. And as you have seen yesterday, as Ravi has shown you, we conduct the consolidation test in a device which is known as audiometer. The mold and the device. This is how this consolidation cell looks like. You have seen yesterday. We keep a sample inside and then we saturate it and then we apply the load and you monitor this settlement and effective stress P. And from this settlement, originally if your sample height normally is 20 mm, then with change in height of settlement, you work out change in void ratio, and initial void ratio you calculate. From that, you plot void ratio versus this P chart. So this is how consolidation cell looks like, and this is how you apply the load. And sometimes you test simultaneously more than one samples also. So this is your sample. This is how you are applying the load, the normal load on this sample, and here you measure the settlements. So this is consolidation test setup in the lab. Now, the test is done on undisturbed soil sample. Yes, it must be done on as undisturbed soil sample as possible. Otherwise, once you disturb the sample, its permeability changes, its void ratio changes, and the whole consolidation parameters changes. So therefore, we must do it in the as undisturbed sample as possible. Yesterday you might have seen there was a chunk sample of clay from which you pick up a small sample. So you can take chunk sample, and from that you can do it. And we do it by applying external load. And once full consolidation is done under that load, then you apply next increment of load, like 24 hours yesterday you for every load increment. And stress applied is measured. You can measure pore water pressure also, so that you know the effective stress. And you check initial void ratio of the sample, either by changing specific gravity or void ratio directly. And by measuring the change in height of specimen, the change in void ratio delta E due to application of load increment is determined. Then once you complete the loading test, most of the time you do unloading test also. I will tell you the reason when we see the graph there. Normally you do loading and then you do unloading also. And then you plot values of stress on logarithmic scale on x side, sigma or effective stress rather sigma dash, and void ratio on y axis. And from that plot, various consolidation parameters. There are various methods: CV, AV, MV, consolidation index, recompression index. There are many indexes which you can work out from that chart. This is how the chart looks like. On y axis you have void ratio, and on x axis effective stress in log scale. And normally this chart comes like this. This blue color one is the chart, and then there are various methods. Like yesterday you used Casagrande method and all. Another method is wherever there is a change in curvature of chart, this is maximum curvature point. This method is also very common. You draw a tangent here, then at this point you draw a horizontal line, then this angle you draw a bisector, and then the second leg after tangent point to this you draw a tangent, and then this tangent and this bisector. This point you take as this side you take as elastic differ domain, and this side you take in inelastic domain, and this is known as compression here. After this, you know, this point. This is within compression line. So after this point, this is known as compression. So its slope will be CC. And if you release this load, as I told you do unloading also, then the chart will be like this. So normally this slope and this slope will be equal. This is known as recompression index. And from this point is taken as pre-consolidation pressure from this point. So before this, whatever was happening was its recompression, and after that it is virgin compression. And this recompression, this slope will be equal to whatever rebound. But there are various methods. I'm not going into detail here for calculating various parameters. But effectively, you use this chart basically. And sometimes this unloading. This is loading chart, and there will be unloading chart. So this is how the consolidation test is done. Okay. Now, there are some areas where this type of soft soils are very common in India. They are very identified areas. There you will mostly find this. Many times there people call it marine clay or various names. They are nothing but different type of soft soils. So all your marine deposit areas, like you go to coastal area, east coast, west coast, all these coastal areas, this you will generally find soft soil. Then river delta deposit areas, where fine alluvial soil will be there. There also you get soft soil. Then these areas of Gulf of Kutch in Gujarat, on the Gujarat coast bottom, that Gulf sort of coast, the Gulf of Kutch, then Gulf of Cambay, same India, Gujarat coast bottom, the Gulf area, east coast of course, any coast, east coast, west coast, both coast, or any other marine area you will have. So these are the commonly known areas. There certainly you will have soft soils when you work there. At few places or other, you will find soft soils and you need to tackle them. There can be other areas also on river banks and all. You may find some areas where soft soil is there, even other isolated locations also. So what is general concept of construction of soft soils? We'll see. Philosophically, what can be done to tackle soft soils, and then we'll see actually what are the methods which are followed in the field for tackling soft soils. Now, as we have seen, the problem in soft soil, there are two. What is that? Number one, their shear strength is less. So if we put a dead load of embankment, there is likelihood that there may be a failure. That is one region, less shear strength, and therefore it cannot take the load. Second thing is settlement. Because of the load, your consolidation settlement will be there and it will continue for a long time. So we want to reduce that. These are the two problems. So conceptually, let us see this cycle. First, let us start from here. This is my ground level and I have to build a bank. Now let us say H is my height of bank. Theoretically, as per my index section or in my project sheet, H meter is height of my bank. Then in all these areas where you have got weak soils, there are some method we'll see as we go along for estimating the settlement. How much will be the settlement? And you must always construct embankment for theoretical height plus settlement. Many times I've seen we make this mistake. On my project sheet, if my bank height is 5 meter, and if I construct 5 meter bank, and if there is a settlement, finally the bank available may be only 4 meter. And then what you will find is top of my bank height is 1 meter less than what it should have been. And in that case, what is the solution? We will see people make it up with ballast. And at all these locations where you have got weak soil problems or weak grounds, you will find that because you're really top level, you have to meet, there will be some fixed points, some turnout, some brace, some level crossing, which are hard points where this much settlement may not happen. And so that point does not go down this much. This point goes down. So for meeting both of them, either you will have sags on approach of all these fixed points, that is your turnouts, level crossing, bridges, all this sort of thing. And something we try to lift the existing track on the ballast, and you will find there is a high, very, very high excessive ballast cushion at those locations, which itself is not desirable. 350 ballast required, that itself is good enough. If you put too thick a ballast cushion, there will be settlement in ballast, number one. And number two, with that ballast cushion, when your ballast spreads at its own angle, your cess becomes inadequate and you will see rolling down of ballast from the cess. So this is a typical byproduct of this malady. If you see in all this new construction, if you have not taken care of the settlement part while constructing our bank, you will find it results into excessive ballast cushions or sags and then ballast rolling down. So first thing, we must always remember this, that we must construct bank to the height plus expected settlement. Now the settlement estimate, as we go along, we'll see there are formulas, but still they are basically approximation. Approximation, there can be 5-10% this side a little bit, but still there are some guides that how much settlement will be there. We can calculate by consolidation theory. So we must always calculate maybe a little bit up and down this side that we can adjust later on. But what I'm trying to tell you is, first thing, you must be very careful that when you construct the bank, don't construct it only for its theoretical height. Please construct it for theoretical height plus expected settlement. Number one. Now let us say you have constructed this bank. Now what will happen? First thing, number one, maybe this bank is stable and your settlement, expected settlement also is also within limit and time is also acceptable. It means no special treatment is required. Fine, it meets all our requirement. Settlement is not very high, bank is stable, there is no shear failure. Then there is no problem, this is the best way out. But as I told you, there can be two problems. First problem can be problem of stability, because my shear strength of this weak soil is very less, and when I put load over that, there may be failures, slow failure in the form of base failures. So for stability, what are various solutions? Number one, we have seen all this, you can put bonds, lateral bonds. With bonds, what will happen? Your stress will reduce, your bank will become wider, your stabilizing moment will increase, and your factor of safety will increase. This is one solution, but we cannot put very wide banks, and with bonds and all, there will be problem of land acquisition and all those. To some extent, yes, first solution, conceptually. Second thing is, you can do construction in stages. This we'll see how it helps. In stages means, let us say my bank is 6 meter, and if I construct bank for 6 meter height, this load my subsoil is not able to take. Let us say this is ground level, and if I construct whole 6 meter bank in one go, maybe soil will not able to take the load and it fails. So what I do is I construct in stages. Maybe first I construct only for 2 meter. Then pore water pressure will be less than 6 meter here, number one, and it is, we are constructing and we are calculated and found it to be within safe limit. Now because of this construction, pore water pressure will develop and it will try to squeeze out. So we wait it till the time that pore water pressure has dissipated sufficiently, may not have become zero, but it has dissipated sufficiently. And in this process of pore water pressure reduction, if you remember, my tau is equal to C plus sigma minus U 10 phi. So when U is increasing, my shear strength is, U is decreasing, shear strength is increasing. So my pore water pressure will go down if I wait for some time, and strength will increase here. Then I put next 2 meter, because now it has got a little bit high strength. So because of that, again once pore water pressure will go up, but this time shear strength is a little bit more, so it is able to take that. And again I wait till there is a sufficient increase in shear strength and reduction in pore water pressure, and then I construct third stage like this. So I have distributed the whole stress and gain in strength over 3 stages rather than doing it one stage. We'll see it in detail. This concept is known as stage construction. Next is, if we can, this always, most of the time may not be possible. If we can reduce the height of embankment, with that what will happen? My load will reduce. Once your dead load reduces, your increase in pore water pressure will reduce. Once that is reduced, your shear strength will be more. So if this is possible, we can do. This is another. They are all theoretically possible solution. Actually, some of them may not be even practical. Next, possibilities I use lightweight fill. Means, let us say my soil weight is 2.65 ton per meter cube or something. I use a material which is very light. If I can, we'll see. There are theoretically there are some possibilities. They may be very costly. When we go to geosynthetics, there are some materials which are very, very light. Maybe if I use those materials, then there will be lesser weight and lesser requirement of shear strength. Next is stone column. By using stone columns, number one, some load is shared by these columns, and second thing is it enhances the consolidation, so gain in strength is faster, and then I'm able to construct the embankment faster. This we also will see in detail. In place of stone column, I can make lime column also. Here also function is more. Nowadays lime columns are not done because lime loses its effectiveness after 1 or 2 years. Or you can, what is known as piled embankment. Below embankment, you put actual concrete pile rather than stone column. So these piles will take part of the load. The design is done in such a way that there is compatibility in strain between pile and your embankment, and your embankment takes only the remainder of the load, the balance of the load, and therefore your embankment is still safer with lesser shear strength also. Or there is a concept called partial replacement or total replacement. It means this was my ground level, and up to here my soil was bad. So either I remove this soil partially or totally and replace it with a better soil. Now with this what will happen? Because I have removed bad soil either partially or fully and replaced it with good soil, now its strength will be better, its settlement will be less, and whole problem is tackled. So these are theoretically possible solutions for tackling the problem of stability. Similarly, for problem of settlement also, many of them are common. Like if you can reduce embankment height, if you can use lightweight fill, or we use stone column, we use lime column, or we use piled embankment, or we do partial replacement, or we do total replacement, or we can make vertical drains. We'll see vertical drains are the drains which helps you in faster consolidation. The consolidation time is reduced significantly, and with that, your whatever settlement has to happen will happen quickly. And after that, you can make up whatever is reduction in bank height, and then you can construct anything, track or something like that. Or there is a concept called temporary surcharge. This also we'll see how it reduces the settlement. You temporarily put some material over that, some surcharge, which will make the consolidation faster. And once consolidation is there, then you remove the surcharge. So these are theoretically various possibilities for reducing the settlement. So now these are the two problems, and these are the likely conceptual solutions possible for these problems, for problem of stability and for problems of settlement. Now we will go on actual. What are the engineering techniques? We'll see in detail now, one by one. What are various engineering techniques which are used for ground improvement in railways specifically? There are some techniques which are there, but we don't use them in railway because of some limitations in our work. Like there is something known as dynamic consolidation, and we normally don't use it. So we'll see what are techniques which are used or employed in railways. So they are broadly removal and replacement, preloading, vertical drains, stone columns, and use of geosynthetics. Broadly, we can divide these techniques into these 5 parts: removal and replacement, preloading, vertical drains, stone columns, and use of geosynthetics. Now we'll see them one by one. Removal and replacement, as I told you, this is the simplest of technique. That if my soil is bad, I remove the bad soil either fully or partly, and I replace it with better soil, a soil which is not compressible, a soil which is not weak. So with that, my strength part is taken care of, and my settlement part is also taken care of. So this technique is one of the oldest and simplest methods. Just remove and replace it. Here, the poor soil, or subsoil rather, is replaced with more competent materials which can improve the soil characteristics. It has their permeability is better, their compressibility is very less, better type of soil. Simple. And sometimes you may require it even in cuttings also, where the available soil below proposed formation level is weak. Even in cuttings also, normally cuttings, it does not happen because as you go down, your soil becomes better. But even then also, in your cutting at proposed formation level, if you have got weak or soft subsoil below that, then there also you may have to use same method, that you remove the bad soil and replace it with a competent soil. And in cuttings, another thing which you may have to take in such cases, that subsurface drainage may have to be improved, because if your soil is weak, and in cuttings, chances of water table being quite near to your proposed formation level are very high. In case of embankment, chances are very, very less, because you are going above the existing ground level. Whereas in case of cutting, you are going below the existing ground level, and most of these places are near river deltas, or they are in coastal area where water table is normally pretty high. So there, when you go to cutting, the water level comes very close to your formation level or something above that. And these soils, when they get mixed with water, they are further treacherous. They are very, very bad when they get mixed with water. Otherwise, also they are bad with water. Their behavior is entirely treacherous. And therefore, in cuttings, in such cases, you may have to take measures for subsurface drainage also. You have to reduce the water table sufficiently away, sufficiently below your formation level, and then you may have to think of some subsurface drainage also there, especially in cuttings. But only limitation of this removal and replacement, people normally call it R&R method, remove and replace method, is this method is generally suitable when soil is up to 2 meter or so. More than 2-3 meter soil, you cannot remove. It's a huge task. If your soil is 2 meter, maybe you pull it 2.5, 3 also maybe come high, but 2 to 3 meter maximum. Up to that depth, either full or partially you can replace. But more than that, many times you find your soil is up to 10 meter, 8 meter, 15 meter like that. Soil is weak or soft. In that case, you cannot do replacement of 8 or 10 meter. You cannot make such a big trench and create a pond and dig another. That becomes almost undoable. Practically not doable. And therefore, this is the limitation of this method. Otherwise, this is most preferable method if you have got only top shallow layer, which is weak or soft subsoil. So in case this method does not work, then next most simple type of method is preloading method. This is also an economical method for accelerated construction, and this also works when layer of soft soil is not very, very deep. Of course, removal and replacement is very shallow layer only, it is suitable 2-3 meter maximum, normally 2, sometimes maybe 3. But this method also is not really very suitable when your soil weak soil layer is 10 or 15 meter, maybe it can be 5 meter, 6 meter, 8 meter. You have to do the calculations. We'll see how calculations are done. And here you do preloading. Here preloading means on existing ground you first apply some load. That will cause consolidation, and once you go to the required consolidation, see, achieving 100% consolidation is very difficult. We'll see also time becomes very, very high. So normally people say at least minimum 70% consolidation we must achieve. That is what. So it depends on how you done. You may design for 70% consolidation, 80%, 90% consolidation. Less than 70% people normally don't accept. So at least 70% also. So you will put on the ground some material, and by that you will achieve 70% consolidation, and then you will construct your bank. So the material which you are putting on the ground can be your normal fill material also. You just dump it there. There will be consolidation, and then you remove that material and same material in layers to make it your embankment of required degree of compaction and dimensions and all. But this technique alone normally is not found to be efficient. It requires very long time. As I told you, if your layer is shallow, then maybe time of consolidation which you work out with this may be within your control. But otherwise, if your layer thickness is a bit higher, and even if you do preloading and all, and you calculate time of consolidation, it may come in 2 years, 1 year. Then it is not really very suitable. So normally this technique, rather than being used alone, it is used in combination with some other techniques. This alone normally is not found sufficient. You use it in combination with something else. And preloading is normally done in 2 ways, 2 forms. One is known as overloading, and another is known as space construction method. One is overloading, as the name suggests. My bank height maybe only 3 meter, my design bank height, but I will put a material or heap the material of the maybe height of 5 meter, 6 meter, more than my bank height. Then only it will give faster consolidation, and then I will wait for 70% consolidation, and then I will remove the material and lay it. So that's why its name is overloading, more than what is finally required. And the second is stage construction method. Stage construction, I told you, you will see in detail also. Both you will do in stage by stage. 6 meter bank is there, you construct 2 meter, 2 meter, 2 meter, or 2.5 meter, 2.5 meter, 1 meter. The stage, how you decide the staging or how you design the staging. So preloading can be 2 type, overloading and stage construction method. Now what you do in overloading? As I told you, in overloading is surcharge. The name is surcharge, which is overload. It is placed on the soft ground. You just bring the material and dump it on the soft ground, and this material weight is more than finally what is going to be your embankment weight. So let us say your embankment height is 3 meter. Here you are not giving dimension only, but roughly your height of this material which you have dumped on the ground will be more than 3 meter. It may be 5 meter, it may be 6 meter, something like that. You put higher than that load. And after a predetermined time lapse, the bank can be built. Now predetermined, we do consolidation calculation. That for 70% consolidation, how much time will be needed? We'll see consolidation calculation tomorrow. How much time is needed? After that time, you remove that soil and maybe same soil using it is suitable. You can build the bank. This is simple overloading method. And as I told you, the magnitude of surcharge and duration you are determined by conventional settlement calculation. Terzaghi's consolidation theory, most commonly accepted theory. There are two, three equations we'll see tomorrow. With that, you can find out for how much consolidation, how much time you will need. So this is how the diagram is. Let us say this side is time on x-axis. So initially, and let us say this is going to be your final embankment height. Okay, so initially you are not building a finished embankment, please understand, as part of overloading, just some height equal to it. Later on you will remove this material and build a proper embankment. So you will start applying this load. This side is load and this side is settlement. And load is proportional to height. Basically, once you come material, load will be in proportion to height. So as you are building height, what you are doing, you are increasing the load. So your load starts increasing. It goes above your proposed height also. See, this is your final load. So that's why it's an overload. And whatever your design value, say magnitude of such charge, at this you will stop. And after this, your load will become constant. Now, if you see the settlement, with this load, settlement will also start. It will start. And even when you reach maximum load, settlement will not stop there. Settlement will continue after this because your consolidation is continuing. And then somewhere, the settlement will become asymptotic, or almost your settlement will stop increasing. This is almost, of course, 100% consolidation. You can take a little bit, or 100% if it is here, you can take a little bit ahead of this. At this time, let us say you achieved your required consolidation. At this time, then you remove this whole thing. And then, maybe using same material, you construct the bank of this much height. Simple. This method we call overloading. Why overloading? Because we are initially loading more than my final bank height and then removing this material. Now, what is the problem of overloading, or what we call single stage construction, is this: that number one, if your bank height is more, let us say even more than 5-6 meters, also not very high, and it is over soft clay of considerable depth, and if you are doing it in single stage, means overloading method, then it will require number one, very flat slopes. Your stability is a problem there. To make your bank stable, you have to give very flat side slopes, 3:1, 3.5, or something, very flat. Of course, you have to do calculation and fine, but you have to give very flat slopes, or you have to make berms or sub-banks, wider sub-banks, to ensure your stability of bank immediately after construction. And both these things makes your construction uneconomical. Unnecessarily making very flat slope and wider sub-banks only for the purpose of taking care of pore water pressure, which is temporary at the end of construction, which is going to reduce in long term, is probably uneconomical method of working. And therefore, this is the limitation of overloading method. When you have to construct banks of little bit more height, or if your soil is very weak, or it is up to quite significant depth, then stage overloading does not remain economical, and you go to stage construction. And stage construction will always followed with observation, means you observe the settlement and pore water pressure. Whenever you do stage construction, it is always with observational methods. It means you observe. You don't go by theoretical calculations alone. There are theoretical calculations, but there are a lot of assumptions in that, and therefore you don't go by them. There are a lot of assumptions, not some will say, and you do actual observations also. So in this, as I told you initially, you build your shear strength in step by step. If your total bank is 6 meter height, first you will construct only 2 meter. So even with lesser shear strength, because your weight is less, your destabilizing force is less, maybe it is able to take care of 2 meter height of bank. And this 2 meter height bank will cause some, like here, I will again repeat, I have told you previously also. This is bank, and let us say this is 6 meter is my height of embankment, and this my soil cannot take 6 meter in one go. Let us say this point. So first I will construct 2 meter. Maybe 2 meter is such a way that it can take this load. So for 2 meter it is safe. And now because of this load of 2 meter, there will be some consolidation, and shear strength will increase than what it was previously. Previously, let us say this was shear strength, now this will become shear strength. So with this increased shear strength, I will put second stage because it can take higher load. Now this also will cause consolidation, and shear strength will increase further. It will become this, and with this I will put final layer. Of course, with all with calculation and checking of safety. This is how we build the strength of bank in stages, by taking advantage of loading in stages. So in this, advantage is taken of increase in shear strength of subsoil due to consolidation by surcharge loading. This is the advantage of stage construction method. Once first stage sufficient consolidation is achieved, I put second stage. Once second sufficient consolidation is achieved, I put the third stage. So here, same diagram which we have seen previously. Now you see, this is time, again this is load, and this is settlement. So first what I will do is I will put first stage here. So there will be settlement, and it will continue further. Now once, and after that I will stop. I will wait. This is my waiting period after first stage. After constructing my stage 1, this is my stage 1. If I call it time T1, this will be my stage 1 waiting period. I will wait. And how I will know? By measuring settlement, I will know that my settlement has started stabilizing here. It means now my stage is ready for taking next load. So I will put second load increment. And this is over here. Again, my settlement will increase, and this increase will continue. Then it will start stabilizing at some stage. That is my readiness for next stage. So I will put third stage. Maybe this is final stage, and then settlement. This is how I have constructed my bank in one stage, second stage, third stage. And if I parallelly plot my pore water pressure diagram, it will be something like this. Somebody is asking what is the waiting period generally. There cannot be any guess. It can be anything from 1 month to years. It has to be calculated. Waiting period depends on how much is your stage height, what is your depth of weak soil, and how much is previous stage. We will see it tomorrow when we calculate it. Yeah, this is third stage. So this is my height, and if I plot settlement with this, it will increase, continue to increase. When it stops increasing, again I put second stage, it will increase. When it again stops increasing, I will put third stage, and it will become stabilized. And if I plot the pore water pressure, so this is my settlement, and this is U. So this was 0, it will increase. Then once this height is achieved, it will start decreasing, and you ideally 0, but at least quite near to 0. Then you will put second stage, again it will increase, it will again go down, and then you will put third stage, again it will increase, and it will go down. This is how it goes. So settlement also, increase in settlement will almost stabilize or reach a limit, and pore water pressure also, either excess pore water pressure will become 0, or normally you don't go to 100% consolidation So maybe you will take 90% or so. It will become around 90% of the original value. Then here you can start building the next stage. This is the concept of stage construction, and this is very very common. This is rather most common. But stage construction alone also does not serve the purpose. When your soil depth of bed soil is very bad, you will find even in stage construction. Let us say if this becomes 1 year, then there is a problem because you cannot wait for 1 year, then 1 year here, 2 year, and 3 years for 6 meter bank. Probably nobody will give you that much of time. So in those cases, what you have to do is you have to use some other method, and normally the stage construction in conjunction with some other method which makes consolidation faster is normally used for consolidation. This is an actual this thing location, actual data of a site where stage construction was done. See here, this is height of bank. These are actual data that was theoretical. This is cumulative settlement. Now you can see here, this is your building of first stage. You have built first stage, and then you are waiting up to here. So from here to here, this is total stage 1. Right? So dates are also given. 31st March 2015. This happened 12th February 2015. But please understand, this is not only due to stage construction. There may be some other thing. Here the gap is only 1 month. Normally in 1 month stage construction will not give this. Similarly, your stage 2 here, then something here, and then you have waited up to here. So this is stage 2. These are actual our railway site, actual observation details. And then third stage, because theoretically we saw horizontal, but everyday progress will not be same. One day maybe you build, and next 3 days you don't build, something like this. So these are various states. You can see this is April to June. Then this is third stage, rise increase, and you have this is waiting period, and this is rainy season also. And then there is stage 4. Some height, and this is stage 4. This bank was done in 4 stages, and you can see these are various stages. This is June, October, and November, and you can see the pattern. See, when bank was going up, your construction settlement was going up. Further also it continues, and at some stage it has started becoming horizontal here. So this is the stage when you put another second round of this. It increases suddenly here. Then again after that it has started stabilizing somewhere here. So then you put third one. Then again it increases. It has started stabilizing here. Here there is not much of increase because this is very less increase here also. So what we were telling theoretically is actually also you can see that this happens like this. These are actual instrumentation readings. And here another thing what you see height is only 6 point something meter, the height of bank. Out of that also your working platform itself is at 1.8 meter height. So after working platform this height is only 4 to 5 meter. Please understand this. And settlement is more than 1 meter. So in 5 meter height of embankment, or maybe take 6 meter, your settlement is as high as 1 meter. You can now get an idea that how significant this consolidation settlements can be. So we cannot afford to ignore them. Otherwise, all your calculations, everything will go haywire. Now, second type of, this is most commonly used things. Along with stage construction, you use some other methods also. These are the major type of methods which are used at the site. Majority of the cases. They are known as vertical drains. As the name suggests, vertical means they are constructed vertically. Their alignment is vertical direction. And drain means they are drains. What is a drain? A drain is a thing which takes water from all around. Let us say surface drain, underground drain, whatever drain when we talk about drain. What is a drain? A drain is one component which takes the water into its own plane, whatever from all around it, and then channelizes in its plane. That is the simple definition of drain. Same thing here also. They are vertical drain. This pore water pressure, which is under excess pressure, is taken by this drain and it facilitates their flow quickly. And because of this quick release of excess pore water pressure, your consolidation time is less. And in less time, you get consolidation and the settlement, and you can complete your construction overall in less time. That's the purpose of vertical drains. You're gaining shear strength. Everything is faster because of consolidation being faster. So we'll see all this. There are various types of vertical drains: sand wicks, cardboard drains, synthetic drain. These are the 4 most common type of vertical drains which are used. And the concept of vertical drain, as I told you, is this. This is your ground. And we know this area is weak soil. It has got very low permeability. Consolidation will take more time. Dissipation of pore water pressure will take time. So I put vertical drains. These vertical drains have got very high permeability. So when this vertical drain was not there, previously let us assume there was a water particle here. Now if this fellow has to go out, it has to travel up to this, and from here only it can go out. Or maybe there is a draining face at the bottom. It depends below this layer. Let us say this green is the bed layer. Below this green layer, if there is a draining ground, then of course it can come either here or here. So maximum travel path of water molecule can be either this full height h. This concept also will use. If it is single draining face, means drainage is only from top, then the drainage path is taken as h. Whereas if drain can be there from bottom also, then drainage path will be h by 2 maximum. So this fellow has to travel all the way from here to here. That too through a soil which is very less permeable. So travel will be a long time taking affair, and then it will get drained out. Now what will happen is these water particles will come here. It has to travel only this much, and they will be trapped by this. This my vertical drain, which is of high permeability, and because of high permeability, it travels very fast. It will come to the top, or if required, it will go to the bottom. And then on top of this area, we construct a drainage blanket. In all these cases, wherever we do ground improvement, a good soil, a free draining soil, not a bad soil, we construct a drainage blanket 1.5 meter or something, or half meter. So this water will come and it will quickly get drained out from here. And because of this, my consolidation will be faster. Whatever settlement has to happen, it will happen. And then over that, I will construct my bank up to my design bank height. This is the principle of this vertical drains. Now we'll see various type of vertical drains one by one. First type is sand drain. And as the name suggests, we make a vertical drain made out of sand. Good free draining sand. So it is a column of about 20 to 30 centimeter dia, which is augured into the ground. So what you do is first you make a hole in the ground of the required depth, pour sand into that, a hole of 20 to 30 centimeter dia, pour sand into this, and over that you put a drainage blanket, and then you put surcharge over that. So because of that surcharge, your pore water pressure will develop, and this pore water will get discharged through your vertical drain, which is made out of sand and the drainage layer. And so column is then filled with sand and connected to a free draining blanket of granular layer. This is how it looks like. In this case, let us say this is impermeable. It can be permeable, impermeable, does not matter. And this is your, let us say, compressible soil, this location, and this is your ground level. So you have to make this sand drain covering this whole length of compressible soil like this. This sand drain can be in square pattern like this, or they can be in triangular pattern also like this. It will make triangles like this. And what should be the spacing and what should be their depth and all. It all depth depends on type of your strata, and the spacing and all you have to calculate. You have to design. We'll see an example tomorrow. You have to design the ground improvement system. And here you will have a drainage blanket of normally half to 1 meter. So and then when you put surcharge over this, when you put any load over this, this water will from this will be quickly it will get discharged through this drains and it will go out like this. So that is the simplest of method. Sand drain basically is made out of sand. And this is how these rigs they look like. If you see, there are degrees by which you drill or auger a hole in the ground and then you pour sand. There were few problems in sand rain. First problem was that this is your ground, and if you make a bore of, and the bore can be 15-20 meter deep also. After that, if there is some collapse of the bore here, or it collapses like this, then you don't know whether this full area has been filled with sand or not. That is one thing. Once you draw out your auger or whatever your boring equipment, there may be collapse of the your bore, and when bore are very deep, it's quite likely. Number one. Number two, it is very difficult to keep account of this sand which is going into this. Very difficult, because of bores, something sometimes it may be less than what you have calculated. Sometimes maybe it sinks here down and more than theoretical calculation, your some sand might have gone. Account is a problem. Third problem is, see what happens, continuity of the drain. If this is your ground level, now when we talk about settlement, in picture it is vertical, but actually the settlement is vertical as well as lateral also. There is a spreading laterally also. So what happens is, let us say I have put a drain like this. This drain will become like this because of settlements, and sometimes it may happen like this also. Maybe this continuity is broken at one or more places because of more lateral deflection and all or distortion. Now if continuity is broken, then drain is of no use. This drain is as good as not being there. This is another problem. Third problem is, of course, by the time consolidation may be over, but still, maybe after some time, this fine grained material, because this weak soil is having more than 50% fine grained content, very fine. Those particles also, they will come with water and they will spoil your sand. And of course, by the time consolidation may take place, but if it has not happened, then this its free draining capacity will be hampered and it is no more functioning as a drain. So these were few problems with sand drains. And therefore, nowadays, even though as a method it is very good, conceptually it is very good, but nowadays you will find that, and now another problem, availability of sand. In fact, nowadays, getting a good granular free draining sand has become difficult and costly, even in the river beds and all those areas, coastal areas also. So all these regions, nowadays you will find that sand drains are not as popular as they used to be maybe 15 years back or so. Another form of sand drain is sand wicks. It is for smaller works and it is used. In sand wicks, what you do is, there you are putting free draining sand in those your bores. Here you fill the sand in some stockings, some bores like this or something, cylindrical stockings, and you first make a bore here and then keep on dropping these stockings here. Or I will make it, let us say, like this, and then you will keep them dropping these things like this, something like this. So rather than using plain sand, you use sand in stockings. What is the advantage? One is accountable is easier. You can count how many stockings are gone, and one stocking volume will be constant. Second thing is, if there is a bigger collapse at the bottom and all, you will get an indication from the top, because then your stocking will not be going down. And third thing is, because you have covered this sand, so the fine particle entering inside sand and spoiling it gets retarded. So these are few advantages in sand wicks. So the sand wicks are ready-made small diameter sand drain, pre-packed filter stockings. They are like cylindrical things filled with sand. And earlier days, woven jute canvas was used as filter stocking. Jute bags, woven. We'll see what is woven, non-woven, and all in geotextile after tomorrow onwards. But presently, synthetic fibers are used for making these stockings. You make the stockings of synthetic fibers and then drop them in this. But this also, really speaking, does not give you much advantage. Number one, whole area is not filled up. There are some cavities which will cause ground movement. Second thing is, when you bore something in the ground and all, it will further aggravate it, sort of a disturbed sort of boring, where again you will cause some disturbance and all. So it is an improved form of sand drain, but sand drain itself, because of various reasons, is not very popular nowadays. Therefore, this also. Another type of thing which is used for some temporary works or maybe when you have to work quickly are cardboard drains. If you see your normal cardboard also, sometime and often you will find your cardboard is basically a corrugated thing like this. Or in vertical direction, if this is from the top, if you are seeing the plan, if you see section, it will be like this. So if you make a roll or maybe something like this of cardboard, like this, and lower it into the drain. But as I told you, this is for temporary and small works. Then this will suck the water from this, and the channels will act as facilitators for water to get drained. And then here you put a drainage filter and you get water out. But then cardboard will decay after some time. This cannot take some load. Of course, it is not normal you're picking cardboard. They are specially treated cardboard. But still, this is for temporary and very small type of works. So this is also one of the type of vertical drains, cardboard drains. These are inserted into the ground by means of mandrel. There are some hollow sections by which you push them into ground, withdraw that hollow section, and this drain remains there. And the channels in cardboard, they facilitate the removal of water. And it will be easy to install and cause little soil disturbance, because you are not disturbing soil much. Only small diameter holes are there in which you put these cardboard rolls or something. So but they are not really suitable for permanent type of work, or at least for temporary work you do at some place and improve the ground, you can do this. And as I told you, this is specially processed cardboard, which has got long life and durability. It's not like normally your paper cardboard or something where we use for packing or making cartons and all, not that cardboard. Next is geosynthetic drain. In fact, these drains are most commonly used drains nowadays. In vertical drain, you will find more often than not, maybe 95% of time people will be using, wherever they use vertical drain, they use geosynthetic drain. What exactly is there in geosynthetic drain? They are also known as PVD, this geosynthetic drain. Their full name is prefabricated vertical drains. They are vertical, so they are vertical drain. They are used as a drain, so named drain. And prefabricated means factory manufactured. You don't have to fabricate at the site. These drains, we'll see in detail. Their dimension is typically, their width is about 95 to 100 mm. Along with geosynthetic, when we discuss geosynthetics, I will show you their samples also. Now I will show you photo. There I will switch on the camera and I will show you actual samples of various products. But I will show you that also. Their width is normally about 100 mm, so 95 to 100, 105, 110, that much it varies. And thickness is only 3 to 5 mm. So what is the advantage of that? Advantage of that is you cause very little disturbance into the ground, because this hole in which, or the bore in which this is going, will be only 100 mm wide by 3 to 4 or 5 mm thick. And therefore, you almost cause no disturbance to the ground, or very little disturbance to the ground for making these sort of bores. And here there is a core in the geosynthetic drain. There is a core material which is corrugated. It is corrugated synthetic core like this, and then all around this there is a sleeve of geotextile, non-woven geotextile sleeve like this. So this is how they are made. They are very light, very easy to handle, but for installing them you require some special techniques. Not really special. With normal excavator and all also you can install them, but on head of excavator, you have to put what is known as a stitcher ring. There are stitchers, I will show you, that you have to put at the head of excavator. That is. So today's date, we really don't call it sophisticated, but it is not normal method that you hammer it or make some hole and pour the sand and all. Not so simple. And their installation poses very little disturbance to the neighboring soils. And another advantage is that large settlement of substrata also, it does not destroy the drain continuity. As I told you, in case of sand drain, like sand drain, if there is a disturbance like this, maybe drain does not remain connected. Whereas they are so thin and so flexible, these PVDs, initially you install like them. After that, even it becomes like this, this continuity will not break because they are very thin and flexible product. So it can take any shape. This shape like this also it can take, and it will still, water continuity will be broken. Maybe its discharge capacity gets reduced, but it will not become dysfunctional. That is another advantage with these drains. So large settlement it can take. This is how these drains they look like. As I told you, this is their synthetic core, which is in corrugated form, and there is a sleeve around them, which is made out of properly designed non-woven geotextile. Non-woven geotextile. We'll see in detail what is non-woven geotextile after another words, but remember this is non-woven geotextile. And they come in roll like this, they are rolled like this, long roll it comes. And this is your excavator. This is stitcher ring, this red color thing what you are seeing here, and it gets mounted there. This roll gets mounted here. Its another end goes into this machine, and through this machine they get planted in the ground. You can see here. In place of sand drain, you will plant this PVDs. You can see here in a series, in square or triangular or whatever pattern which you have designed for your system, right? Like this. This is stitcher ring, and one after one. It takes very less time. Very less time. Very simple, but very effective technique. That's why that's the reason that they have become very popular now. I will show you two things. First, I will show you an animation which explains how this works.
Prefabricated vertical drains consist of a specially designed synthetic core, which conducts maximum water flow along the length of the drain. The core is fully wrapped in a durable geotextile filter jacket that has a very high water permeability and excellent filtration properties. Both the core and the geotextile filter jacket have high mechanics of strength and durability. An anchor plate is attached to the end of the PVD. To achieve each installation, PVDs are installed into the ground using a hollow mandrel that houses and protects the PVD material. The mandrel is then hydraulically pushed into the ground by our installation rig in accordance with the specifications established by the contractor's engineering team. Once the PVD has been driven to the correct depth and pressure, the mandrel is then withdrawn back into the mast, leaving the PVD in place. The rig then moves to the next predetermined installation location and continues the process. The installation details for each PVD are verified by the operator via Soilwick's industry-leading in-cabin measuring and recording technology. Once the PVD installation has been completed, a new surcharge layer of loading is applied to the site. This surcharge layer, combined with the PVDs, accelerates the consolidation of the subsoils so that it occurs over a period of months as opposed to a period of years. Correctly installed prefabricated vertical drains significantly reduce settlement time, allowing the construction process, in this case a freeway, to be completed in a far more cost-effective, safer and faster time frame than traditional methods.
Okay, you are able to get the voice of video also, no? Hello?
Yes,
okay, right. Yes, sir. Okay. So now this was about principle, how PVD is used. Now I will show you an actual, our own railway site. This was, I think, we have taken this photo in Dublin between Ernakulam and Kottayam. Their actual site, somewhere near Ernakulam, this work was going on. You can see actually how it works. This is your rig. This is your PVD hole, what you can see here. So, now this is the mandrel which is going down. You can see this wall is being controlled. And you take it down to either your design test or point of refusal. Now it has reached point of refusal. That's all. Now this mandrel is being withdrawn and PVD gets planted there. You can see here. That's all. And you cut it little bit above the ground level because here you will put that drainage blanket. Already some part there, some more part there. And that's all. So maybe 4 or 5 minutes, not more than that. One PVD depending on depth. Very easy and very simple, very fast work, and it is so effective that some of the places where water table is high, we have seen that immediately after putting PVD, even without putting surcharge also, even with normal ground load, and there is so much of water pressure that you will see water oozing out from this PVD. See, this is one such place you can see here. See here, from this PVD you can see water is coming out. It is dripping. So effective. Whereas you are not putting a full surcharge load. So then even with the load of this excavator or the equipment which are moving over that, you will get itself, you see that much of water is being drained out. So they are very effective and very easy to install. That's exactly the reason I told you they have become almost all vertical drains nowadays. Wherever it is done, they are done in the form of PVDs. Now I will tell you some, because we've got many case histories, but some 2-3 very typical sort of case histories in our own railway applications where how PVD has solved the problem. This first is one of the earliest recorded and scientifically done case history. Maybe before this also PVD might have been. No, this is one of the earliest. This was for subsoil stabilization over Ennore Creek. This is in Southern Railway Chennai Division. This was for 3rd and 4th line between Korukupet Attipattu in Chennai Gudu section of Southern Railway Chennai Division. This was done during work was done in 2008. So this is one of the oldest and still working around 10-12 years. Of course, here once consolidation takes place, then it will work, and consolidation takes place within the next few months or maybe a year. Here, actually, if there are people from Southern Railway, some of you may be familiar with this site. This is a creek area where the existing 2 lines also were creek. And for 3rd and 4th line also, you have reclaimed, we have created the land by reclamation. So below that will be all marine clay, below whatever you have put extra. And here, actual ground was soft marine clay. And how much soft you can imagine its N value was 0 to 1. Means most of the places 0, maximum which they were getting is 1. So now you can understand how bad this soil would have been. And this depth of soil was 10 to 15 meter below seabed. Seabed itself will be 3, 4, 5 meter or whatever. Below that, 10 to 15 meter, up to 15 meter depth, this sort of marine clay was there. So very bad location. And in normal course, it was difficult to construct the bank. And if you have done normal loading, means you do surcharge loading and then wait for consolidation or whatever, then the time calculated would have been around 5 to 6 years. So 6 years you could not have done earthwork there. And nowadays, not even nowadays, nobody will listen to us if you say that I want to construct a surcharge bank and wait for 5 years. Nobody is having that much of patience, and rightly so. So they employed PVD and preloading method, stage construction and PVD, both simultaneous. Mostly this is the sequence. And to avoid shear failure of the embankment, in addition to PVD, they also provided a geotextile layer on top of existing ground at the bottom of embankment. These are method of various design methods for geotextile. Using geotextile when you do slope, as I told you in slope stability analysis, you can see by putting a geotextile layer there whether you are getting advantage or not. If you are getting, you put it, or you can put geogrid, or you can put geocomposite, depending on what is your requirement and what you are looking for. This is how this site was. This is existing two lines, and this is of course pathway for reaching there. And here the third and fourth line were being made. You can see here. This is the reclaimed area, and this is creek. These are PVDs. You can see PVD here. This PVD work has been done. And if you see the section, this was existing embankment. Okay, some sort of embankment protection, pitching and all against displacing water is there. Then this is your seabed, very soft marine clay, and below that also firm stiff clay. So they have filled this area also in normal soil, and then they have done the sand fill here on this natural ground level. This is actually the drainage layer through which water will be drained out. And these are the PVDs at 1.25 meter center to center, triangular pattern. They have provided the PVDs. These are the PVDs. This PVD they terminate into this drainage layer, and on top of that, this is that I will remove another clutter from here so that you can see. This is your geotextile layer. This one on the top of embankment or the bottom of embankment and top of ground, and this is extended embankment. Height is 5 meter, and they have kept only 2:1 slope. See, otherwise you need very flat slope, 2:1 minimum. And they did in two stages. First stage up to 3 meter height, and second stage for 2 meters. So this is 2 meter, and this is 3 meter. And from bottom up 1 meter, they have filled with this 1 meter drainage blanket. And here they have put some bamboo piles and some sandbags, so that there is no erosion of because of wave action. This is how this was the system, and this is ground improvement which they used. PVD at 1.5 meter center to center, triangular pattern. And with this, they were able to complete in few months' time. It worked well, and even now it is continuing. And these are actual reports. Actual, as I told you, whenever we do stage construction or PVD or anything, observation is must. We may do theoretical calculation and say this will be settlement, this will be pore water pressure dissipation time, but there are a lot of variables in that, there are a lot of assumptions. So proof of pudding is in eating. That gives you an idea that it may happen on 30th or 35th day, but this 35th day can become 25th also, it can become 50th day also, 45th also. So actually we measure at the site and confirm that yes, this has happened, or so much of stabilization has happened. So settlement and pore water pressure, at least these two are bare minimum. We'll see at the end what are other instrumentation, but these two instrumentation, dissipation of pore water pressure by using piezometers and settlement gauges for measuring settlement, they are must. So this is settlement record, this site is base, this is cumulative settlement. Now they have put 3 gauges at 3 different places. You can see here, there's some expected pattern SG1, SG9, SG14, and it has stabilized here, you can see here. So in 150 days, as against 5-6 months, in 150 days, your site has been stabilized. You can see. So 5 years or 6 years to 5 months. This is the difference by faster consolidation. Here they have plotted predicted versus actual settlement. Also, this is of course for theoretical purpose. This is the number of days and at a particular location. Now, even this also, whenever you have this drainage through this vertical drains, one is vertical drainage like this. In addition to this, there is radial drainage also. So in calculation, what they are trying to show is radial drainage is also important, and it has got a significant effect. So if you take only vertical drainage, then your degree of consolidation, this side, the chart would have been like this, theoretical, okay, without PVD or something, normal. Then PVD for combined radial and vertical drainage. Now there is a coefficient of consolidation, and coefficient of consolidation in vertical direction is CV, in horizontal direction CH. Normally your CH is more than CV, but for that you have to do a directional permeability test, which is difficult. So many times for the sake of simplicity, you assume CH equal to CV. So if you assume CH equal to CV, then this will be your predicted degree of consolidation. And if you assume CH equal to 3 times CV, then this is your predicted degree of consolidation chart, and this firm line is actual chart. So what they are trying to say is that if you can do permeability test, directional permeability test for horizontal direction, in that case, and if your CH is more than CV, you can take advantage of this time also. Otherwise, in normal case, I would have assumed, let us say I have to get 70% consolidation. Draw a line here. By my normal calculation, I would have taken 160 days. Actually, it is 60 days only. In 60 days, I'm getting this much, provided that I have data of CH also. We will see in our calculations. We have got different parameters CH and CV. If you have got values of both, you can take advantage of that CH also. Otherwise, you will be on safer side only, but you will be giving more time than what is required. So this is about this side. Second case history is about, there is an station yard by name Udaipur in NF Railway in Tripura. This is after Agartala, new line after Agartala. To Agartala it was GS conversion, the new line extension from Agartala towards Sabroom, I think. Agartala Sabroom, yeah. So there is a major station there, Udaipur station yard. This is second case history. In this, the height of embankment, the design height is 6.2 meter. And they started embankment construction in 2010 without any ground improvement. First, no ground improvement was planned. So like normal embankment, we started building the embankment. 6.2 meter height. Please remember these figures. Then, when the embankment height reached around 3.5 meter, number of failures started. The bank started sleeping. There were base failures, and for nearly 1 year, September 11 to December 12, they were not able to construct the bank. They used to repair, construct, again fail, repair, construct, fail, and there used to be base failure with heaving going up to 30 meter distance from top bank. As I was telling you, normally this heaving occurs far away from the bank, where the slip circle may be striking your normal ground level. So there was heaving, classical case of shear strength failure, base failure. Then when problem became severe, they gave a consultancy to IIT Guwahati for detailed geotechnical and hydrological investigation. And I don't know, it must have been known, but later on it was confirmed that where the bank is being constructed is actually a lake. And lake bottoms and all this water bodies bottom will have stiff clay or clay, very poor type of clay. And water level during monsoon goes up to 3 to 4 meter above the existing ground level. So 6 meters is your bank height. Water level will cover 3-4 meter of that. And before going to water level at 3-4 meter, only all your failures have started taking place. And the depth of soft clay is 9 to 13 meter below existing ground level, quite significant depth. So what they did, they took consultancy from IIT Guwahati, and what they suggested, first of course, whenever there is a bank which has failed, first thing which is done is strip away everything whatever you have done, bring it back to wherever existing ground level was there, then do ground improvement and reconstruct the bank everywhere. That is the methodology. It is not that half-slip bank is constructed again and something. You should not attempt that also. So strip the embankment, construct it, and rebuild it after proper ground improvement measures. And they evaluated various methods, PVD, stone column, and all, and finally they found that PVD will be suitable. Normally this is the sequence. First you evaluate PVD. If PVD is also not working, then you go to stone column. That is final thing. Because stone column makes it very strong, but they are very costly, very, very costly. So if PVD works, then we must always go for PVD or vertical tape. And this is the details of PVD. They provided PVD in triangular pattern. Spacing was 0.8 meter center to center. Then over ground, first 150 mm porous sand layer, right? With top of PVD in this layer. So first 150 mm porous sand layer. Over this, a layer of non-woven geotextile. Over that, again a 300 mm thick layer of coarse granular material, and then a woven geotextile. So over ground, effectively around, you can see around 0.5 meter depth of sand, 150 plus 300, and one layer of non-woven and one of woven. Why woven and non-woven? Of course, we'll see when we go into geosynthetic. Woven geotextile gives you good shear strength, and non-woven geotextile is a good drainage element. It helps you in drainage. So that's why they have put one layer of it. Then stage construction. The bank, they said you must construct in stages with sufficient time between each stage. Of course, the stage time, as I told you, first we calculate theoretically, but we never go purely by those calculations only. You measure the settlements. So monitoring of settlements using plate type settlement gauges and pore water pressure with Casagrande type piezometer. So there are settlement gauges, piezometers are used, and Casagrande type piezometer are most commonly used piezometer. They measure the pore water pressure, and when they confirm you that your required degree of consolidation for which you have designed your stages, which can be 70 to 90%. Normally, as I told you, nobody works in less than 70% degree of consolidation, and normally maximum you try to get 90% before constructing next stage. So that confirmation is by actual observations and not merely by theoretical calculations. And here, of course, they took 95% consolidation in the typification of design, and it took around 100 days. And you can see total settlement was 1242. In 6.2 meter bank, settlement is 1242, 16215. This was I have been telling previously also that settlement in these soils is very significant. It is not a small amount of settlement. This is how it was. You can see here, this is the existing ground level. These are the PVDs. They are in triangular pattern at 0.8 meter center to center. This is your drainage blanket. In this drainage blanket, first 150 mm sand, then this is 150 mm porous sand, then non-woven geotextile, then 300 mm another not sand but free draining soil, and then woven geotextile on the top as base first here. And on this is a normal bank, and see 2:1 they are able to construct and make it safe. Otherwise, it will be very flat. So this is what was done. And this is soft clay layer, I told you 9 to 13 meter. And then of course proper berms wherever needed, and drainage system and slope protection for rebuild embankment, whatever turfing and also protection they were done. And then they say advisable to build entire space and area up to 2 meter height before reaching full embankment height. It means two stages. First stage of 2 meter height and second stage of balance height 4 meter or something. This was the design. And after first stage of 2 meter, wait for 100 days. Roughly it was 100 days, and then build next stage. This was done, work completed, and this is commissioned for many years now, and it is working satisfactorily. This was between these two stations, Vaikam Road and Karukantara. It is in Trivandrum division. This is the Chennai, and this was part of Ernakulam, Kottayam, Kayamkulam doubling in Southern Railway. There were many bank failures here, not one. And we gave consultancy in two stages, one for 5 banks. This is one of them. Others were similar, so I have not put it here. Now here, how was the scene? I will explain to you. This site is located on Vaikam Road side approach of Kaduturthi river. In fact, there is a river by name Kaduturthi. Both approaches there was problem of this river, towards Vaikam Road side and towards Karukantara. So this is first side, towards Vaikam Road side, that is what I am telling you. Height of existing bank, this was doubling. So there was an existing bank. Existing bank height was 3 meter and new bank was 5 meter. This is your existing bank. This is of 3 meter height. And new bank is something like this. This happens in most of the doubling project. This is how it happens. Of course, here center to center was far away because of major bridge. This is how it was. Now, this is soil investigation report there. Now, this cannot be true. That is what another thing which I want to tell. I will tell you. Soil investigation report must be proper. There is something wrong. Either wrong report has come or report was not proper. As per that report, it says up to 6 meter depth. It is sandy clay silt. Sandy clay silt is good enough soil. It's not a weak soil. And N value between 8 to 12. And allowable bearing capacity estimated there. This is as per geotechnical investigation report. Is 4 ton per square meter at 1.5 meter depth and 12 ton per square meter at 6 meter depth. 12 ton per square meter is a very good bearing capacity. And if this is true, your bank can never fail. I can tell you. The region bank has failed when this is not true. Either it was in dry season or at some other place, report was done and copied here or by mistake or by mistake, whatever. But this cannot be true. That is what only thing I want to tell here. Now, once they constructed full bank, on construction of full bank, there was failure of new bank with heaving of ground on west. When they constructed this full bank, there was a failure like this. This whole thing failed, slided like this, and there was a heaving here. Now, when this thing slided, previously this bank was leaning against this bank. When this slided, what happened in the existing track also, it went down and it shifted like this. This happens most of the locations in doubling when it happens. When this bank fails, the existing rejected between them here. And when this portion suddenly becomes vacant, this will also have a tendency to move like this because there is some earth pressure here. Acting which suddenly gets released. So this will go down and this will go side towards this. And this is what happened here also. Then fill material was removed, as I told you in most of this done, and a technical consultancy was taken, and this technical consultancy was proof checked and approved by IIT Madras. This is how you can see. This is of course later on. This is new bank which has come up after repair of these banks and all. Here you can still see some remnants of this. This is your existing bank. This point and this point were with some grade. They were almost. This is photo taken standing from the bridge, and after that station is there. You can see signal and all. They were almost at the same level, and now you can see this point has gone down, and failure was this side. So this has gone like this towards. Of course, this bank was repaired. There were 4 or 5 locations where this had happened. At other places, of course, this was repaired. I think 1 or 2 places still it remained for quite long time. I don't know presently what is the situation. So this they have repaired, of course, and it came up properly. There was no problem, but this remained there. Now, what are the recommendations in consultancy report? The recommendations are quite similar most of the places. They recommended PVD at 0.8 meter center to center in triangular pattern, and they said after providing PVD, provide drainage filter, then lay high strength geotextile at the base, and construct embankment for 3.5 meter height in stage 1 and balance 1.5 meter in stage 2. And here they designed for 70% consolidation. So they said after 70% consolidation, which theoretically will happen in about 1.5 months, but actual instrumentation should be done at the site, and then you must go for stage 2. So this is stage 1 waiting time. And degree of consolidation achieved in each stage shall be evaluated using actual settlement data and core pressure data. This is very, very important. In fact, at this site, then bank was constructed successfully with monitoring of settlement by pressure, by settlement gauge and cassette gauge. And I was there were 4 or 5 banks in this. So nearly 1 year or more than that, I was monitoring it, being in contact with chief engineer construction and CEOs are there, and there was absolutely no problem. Of course, now it was commissioned in 2016. So now we are almost 4 years over. There should not be any problem now. And after settlement, they recorded the fat for place. This you can see. This is after rectification and everything. This is new bank. There is absolutely no problem. Of course, this existing bank you can see the problem still it continues there because that could not be attended. And these are the settlement gauges. We will see also that there is the most common type platform type settlement gauge. Here there is a pipe which goes down, and there is a pedestal at the bottom of the embankment somewhere. And this is another casing pipe which is in the side, and on top you put some lid like this. Very simple type of gauge. And you measure the difference between this pipe and this pipe level by putting a scale. This is top of this pipe. This is another pipe. By putting a scale here, you measure the level, and this is settlement. And you keep on recording settlement. There are frequencies you will see, and you plot the cumulative settlement. Very simple. Similarly, cassette type piezometers are there that you of course embed in the ground, and there is only a lead outside that you put to readout unit and you take the readings. So come to stone columns. Now, stone column again is it you make a bore in the ground, and previously we were putting sand. Here rather than putting sand, you put stone. So you make it out of well-graded granular material, and the property of that material should be it must be having high angle of internal friction, it must be chemically inert, it must be hard, and it must be preferably angular in shape. So your stone, like stone ballast, fits that requirement. There is a separate IS code for material for stone column. If you see there, it looks just like ballast. Only thing is size is little bit bigger than your ballast, and that meets all the requirement. So you make a hole in the ground, you auger or bore a hole in the ground, and put stone column there. Sometime in place of stone column, now sand columns are also. There is a difference between sand drain and sand column. Please understand. In sand drain, you just pour the sand into that, whereas in sand drain it is put into a different way. You'll see that. But most popular are stone columns. And what happens is, let us say this is your ground. Your sand drain and all they are not supposed to take any load. They are just supposed to deform with the ground and only provide you consolidation. Whereas in stone columns, see, previously let us say this is your stone column, and they will be a little bit protruding above the ground. So when you apply the load of embankment, first this will take more load, and your ground will take less load. So with that, what will happen? Deflection in this will be more, and deflection in less, this will be less. So this deflection is more. Once it deflects more, load will reduce in this, it will increase in this. This is between two stiffness, there will be a balance after some time, and then after some time there will be uniform equitable distribution in proportion to their stiffness. You must be knowing that your columns or beam. If load is being shared between the two material, they share the load in proportion to their stiffness. The stiffer material will take more load, and the flexible material will take lesser load. So in proportion to their stiffness, then load balancing will be there. So initially a large portion of load is initially resisted by stone column and balanced by this cohesive type of weak soil, and then the variation in load sharing takes place till strain in both the material, they achieve compatibility and equilibrium conditions are attained. They start sharing in proportion to their stiffness. They will start sharing the load, and this is called their interaction with soil. So they interact with soil and increase the shear strength and decrease compressibility. See, that is the difference between stone column and your other vertical drains. Other vertical drains are not designed, and normally they don't take vertical load. They only expedite consolidation. Now let us say after full consolidation also, after full shear strength you have gained, and still your shear strength of soil is not sufficient to take load of your embankment or superstructure, then what you do? Then your vertical drain is insufficient. That is where you use stone column. Stone column not only increases consolidation, it makes consolidation faster and thereby helps in faster gaining of shear strength, but it also takes some load, and therefore your bearing capacity also increases. So it helps in load sharing also. That is the additional advantage of stone column as compared to your vertical drain. So where your vertical drain fails, it means you calculate as per your consolidation theory. Tomorrow we'll see that after everything also your shear strength is not coming sufficiently required value, and you are failing. In that case, you have to go for stone column or piled embankment. This is basic difference between vertical drains and these stone columns. And as I told you, also act as a drain, thereby accelerating consolidation and minimizing post-consolidation, post-construction settlement. So whatever function of vertical drain they do, in addition, they provide you extra load sharing capability, which increases your bearing capacity of the ground. So there are various techniques by which you put stone columns in the ground. The most commonly used technique is known as vibro flotation technique. This is the most common technique. In fact, to tell you the story, the most commonly the stone columns, they were first started in just. So in this vibro flotation technique, see what happens is again there is an arm, there is a rig. This rig has got one penetration tool which goes into the ground. Then it is hollow also from the top, from which you can drop this stone. I will show you some animation and videos also. So you bring this to the site, and then by using this penetration tool, you make your bore. And you use compressed air also. In this you press compressed. So wherever any resistance is coming to ground penetration and you want to penetrate more, then you use compressed air here, and that reduces the resistance and pushes it down. So you will go up to the required level, up to whatever level you have to go. Then you feed stone from this. So this stone will come and fall here, and then you will withdraw this penetration tool a little bit up. You will bring it up to here, so the stone will fall here, and then again using this pressurized air, you will pressurize and put pressure on the stone. So if original volume was this, it inflates and becomes volume like this. So this will become its volume. So like that, series by series, you will withdraw and construct the full stone column like this. Then next column, like that, one by one, you will construct the column. This technique is known as vibro because by vibration, in floating condition you come and you drop the material there, and in floating condition you do the vibration of the dropped material. So you not only drop the stone, you do its vibration also. So it expands sideways a little bit than the original dia of the hole, and takes care of your lateral expansion of soil also. This is how, see, this is railway line on side of that, you can see the series of stone columns like this. They are also in triangular pattern, or they can be in rectangular pattern like your any other ground improvement measure. And over this you will construct your drainage platform and your normal embankment. Now just to show you working this, there is an animation about how this technique works. Stone column. There is no sound in this. See, this is the tool. Here the compressed air comes. So you keep on, one is with vertical pressure and then with compressed air. Using both, you penetrate the required depth of subsoil. Here, let us say you come to the required depth. then you will charge. This is your stone. This is just a little bit bigger than our track ballast. If you see its IS specification, you put it in this hopper which is on top of this tool. Now through this vertical pipe, it will go to the bottom of your borehole. Here, and like this. Slowly, you will keep on moving this up and keep on rubbing stone and then pressurizing from top so that laterally it expands. Like this. And like this you construct series of stone columns, one after another. But takes more time, significantly more time than PVD, and quite costly. Like this. You construct a series of stone columns. Okay, so this is about concept of this. This is an actual site where I will show you. This is an actual RVNL site in Southeastern Railway, Panchkuda Haldia, third line, doubling, Panchkuda Haldia doubling, which RVNL was doing. There they have done stone column work at one place. Here you can see this is your group which has started being pushed to the ground. The point is going down. You can see. This is closer. This is compressed air, just the move one you show. What's compressed air? Whenever you find it with resistance, it pushes like compressed air. Now it's being freezed to the required. This is also compressed air. Now you have started withdrawing it and you can see this is the ballast or stone which is used. Okay, so this is actual stone column video. There is another technique of stone column also, which is not very common, but there is a technique called ramming technique. In this technique, what you do is first you drill the bore up to required depth. Sometime maybe you may use some casing also if your bore is collapsing. There is another one casing is not required because your tool is always available there. Then you remove this boring thing, whatever feature valve you use, and you put some stone and then you ram it from the top, around 60 centimeter in this case per stage. Then you put some more stone and ram it like that stage by stage. You keep on going up like this. You are going till your whole thing comes. This is for cello depth and all, but not very common because number one, you have to put casing and all, so it does not laterally, it cannot inflate, and then stabilizing borehole and all are problem. Third type of thing is sand compaction pipe. This is different from sand vertical drains. Listeners, they are very sophisticated, very costly. Very rarely it has been used in India. Here, everything is more or less same like your stone column vibro-flotation technique. Only thing is rather than stone, you put sand there. So here, these are the rigs. They are very sophisticated rig. This rig goes down, and this driving casing pipe into the soft ground. You will drive your casing pile or rig there. Then you will withdraw the casing pipe and bottom feeding sand pile. Casing pipe will be withdrawn, and then you will drop sand from the top, and you will like your stone column. You will keep on withdrawing your penetrating tool, and you will keep on pressurizing the sand also in stages so that it will expand like this, and like that you will keep on going up to the top, and you will fill up your whole of the borehole. So this is quite similar to stone column. Let me say in India it has not been very popular. This is one of the technique, but it is different from vertical drain made of sand where you simply pour the sand. They are sand compaction pipes. Now this is a case history. It's again a case history of stone column in Indian Railway. This was between station Kesapur Maisadal in Panchkuda Haldia doubling in Southeastern Railway. As I told you, it was executed by RVNL, and history was something like this. The new bank for doubling, its height was about 9 meters, and it was quite away from the existing line because there was a old station and there was an RUB, and also both lines were quite apart in this case, 30 meter apart. And then in the year 2011-12, out of this bank up to 3 meter height bank was constructed at Chennai 7270 to 7720. Out of 9 meter, your 3.5 meter height is constructed there in the middle of your section because there was Marcy area and all. And this patch was used as excess in the block section. So this is, let us say, single line. For double line, they did some work for bank here, and this used for feeding further the material in your section. So this was what was done. And see the timelines, it is in year 2011-12. Then here width of bank was 6.85 meter as per earlier standard, not 7.85. And side slope was 2 horizontal is to 1 vertical up to 6 meter height. And after 6 meter height, wherever it was more, a 3 meter wide bomb was provided, and slope was also flattened to 2.5 horizontal is to 1 vertical above 6 meter. Right. Then in year 2013-14, see in 11-12 first 1 year only 3.5 meter height was done. Then in a very short time, just when commissioning was nearing, when works get speeded up, the balance height of the bank, which is 5.5 meter, and blanketing etc. were done in about 3 months time itself. So balance 5 to 6 meter was built up in 3 months time. It means very fast it was done. And during this, there were major failures of the bank with base failure at these changes 7220 to 705. These are the dates. Then at this channel 75220 to this date, and there was a heaving on the side. The heaving height was about 1.25 meter. As I told you, most of the base failure you always see the heaving on the side of your bank. Maybe quite away, but you will see signs of it. This is how it looks like. This is failed bank you can see, and this is failed bank, and this is away from the bank. This the brown color thing, gray sort of thing. This is heaving. Of course, here on that some grass has grown, so it is not visible. Wherever grass is removed, you can see a gray color thing. This is heaving, and why it is gray color also there is history. We will realize just now. So an investigation was done, and of course, cause was found that because of fast pace of construction, it did not allow the pore pressure to dissipate and resulted into base failure, your shear strut failure. And subsoil investigation, these are the results. See, on top, up to this 0 to 2.8 meter height, up to this height, you see filled up by soil, fly ash, grey silty clay and all what it is. there previously when single line was constructed, there also there was a problem. We'll see later on. And for taking care of that, that time steam loco time was there. There was some major stream in Kharagpur or somewhere. Panchkuta, there must have been a major steam loco set. So from there, the cinder and fly ash, which was readily available, which is a granular material, cohesionless material, it was filled and a very wide bank was constructed. So this is the filled up toe material, and this only is showing in that heaving. What gray color is because of this. And this is the problematic layer from 2.8 meter to 11.6 meter. So 8.2 meter depth is your problematic layer, and you can see N value is 0.24 and liquid limit 57, plastic limit 28, C value only 1.7, bulk density also very less 1.68. This is the root cause of all the problem. Below this, even though it is clay, but N value is good. C also has improved, liquid limit, plastic limits also, as you see, as you are going down, it is coming down. Bearing capacity is increasing. So this tells that this is general pattern. So this is the problematic layer. So whatever ground improvement you have to do, it must go up to this depth. This is how from soil investigation you will be able to find out. Now, and on investigation, they found out the area where the filled up area, it was actually a water body, it was a pond. And water table, that area is coastal area, very near to coast, just 1 meter above existing ground level, 1 meter below. So very high water table. So it will mostly in saturated condition. And then they also found out that similar problem was faced when single line was constructed there in 1969. The existing single line was constructed in 1969. That time also there was same problem. But that time all these techniques were not so commonly used and not available. So what they did was, number they constructed very wide bank so that your stress is less. So if you remember, conceptually initially I told you construction of wide bank also can be one of the solutions. But nowadays we will not like to do it for the sake of economy. And then they used the cinder steam loco ash, which is actually granular material, as fill material. So it allowed the drainage. And for this work, a technical consultancy was taken, and recommendations of this consultancy were verified by independent consultant Jarwar Saab, our XME, very renowned and very technically sound person. पहले consultants ने किया, फिर Jarwar Saab ने उसको check करके अपने comments दिए, कुछ modify कराया, and then they took RDS also. They involved in finalizing the construction scheme after consultants check and all. They gave it to RDS also. Our people also went there, and there they found that number one, preloading takes very long time. We cannot wait up to the time. It is an urgent project for port connectivity, and PVD was found unsuitable due to very poor bearing capacity of the subsoil. They did calculation and find out that even if you do PVD, after PVD also whatever strength, shear strength improved you get is not sufficient, and therefore PVD is not the final solution, and therefore they have to switch over to stone column. This is how the logical way of doing the thing. This is how it must be done. And then these were the final recommendations. The stone column again 600 mm dia at 1.6 meter center to center for bank height up to 6 meter, and 2 meter center to center for bank height up to above 6 meter. So wherever bank height is less than 6 meter, dia is 1.6. Wherever it is more than 6 meter, dia is 2 meter center to center. And they must be in square grid pattern and up to 5 meter beyond the toe frame. And this is another very important thing. If this is your bank, and if you are doing any ground improvement, this is not line of control or line of actual control with China that we stop over ground improvement here. No, effect continues this side also. So you must continue your ground improvement to some. I will tell you how much it is as we go along afterwards, but it has to continue some distance beyond toe of embankment also. It is very important. Okay. So here they went up to 5 meter beyond the toe of embankment. Okay, that's 2. Bank height is 9 meter or something, so 5 meter. Then over that they put 0.5 meter thick drainage blanket of sand, and this blanket also was extended to half meter beyond toe of bank. This also is important. This is your bank. Here, this is your drainage blanket. If you stop drainage blanket just here, what will happen? This water coming through here will get discharged right at the toe, and it will start cutting the toe. Therefore, you always take about half meter here so that water drains out here and it does not start undercutting your toe. And side slope was made 3 horizontal is to 1 vertical, and there was a berm of 3 meter width after 4 meter height from the top. So from top you start 4 meter, then 3 meter width, and then 5 meter height below that. And within H plus 3 meter, as we have seen earlier, we should not have pond or any water retaining thing. So whatever depressions, ponds were there, they were filled up with locally available material. And then they did turfing on bank with pro slope drain and everything, normal bank protection. This is the scheme. This is existing bank. This was new bank. So 3 is to 1 slope, then berm up to 4 meter height. Below that, again second 4 meter height, then 1 more berm, then like this. And within H plus 3 meter, whatever response are there, they were filled up. These are stone columns, and they go 5 meter behind after toe of bank also, and this drainage blanket goes half meter after toe of bank. This is the working scheme. And then they, in fact, there is an IS code also, IS 15284. Whenever we do stone column work, we have to check their effectiveness by the plate load test. There is a plate load test for stone column work, and these are the tests. The only thing I want to tell is, without doing stone column work, when plate load test was done, its bearing capacity of the strata was 2.2 ton per square meter, and these are the values after doing stone column work. You can see almost 5 to 6 times increase. 12.35, 11, 12, 11, 12, 11, 12. So this is the advantage of stone column. Not only it gives you faster consolidation, this is the biggest advantage of stone column. It increases your bearing capacity tremendously, and therefore load on your bank quite significant distance gets shared by stone column also. And these are the data. Primary settlement consolidation was calculated as 163 mm. The stone column settlement will be less because it takes a lot of load. And secondary settlement was calculated as 73 mm. But actual settlement were measured at 175 and 85, and still it was continuing. So it means again your calculated value will mostly not be equal to actual value. There will always be some deviation. There will always be some variations between the two. And then as usual, any observational method they provided settlement gauges 8 numbers at 3 meter from center line of proposed track, and settlement readings were taken thrice a week till the settlement stabilized. And this section, in fact, which was so troublesome, everybody was so much worried. When it was inspected by CRS, they were able to do speed trial with 115 kmph speed satisfactorily without absolutely any problem. And it was opened in November 2015. Now almost 4.5 years out. There is no problem. So this was, and this is last thing. This is today's last slide. Then we'll close this tomorrow. This is the photo of the place. There is an RUB also there. This standpoint, and this is the bank. You can see. They are of course turfing, and they have provided vertical drains also on the slope for water to come out at every 50 meter and all. Nicely, standing nicely, and a good work done, and has given very good results. So basically we can divide them up. There can be many uses, but what is most commonly used techniques? Use of geosynthetics 3 ways. One is use of prefabricated vertical drain. This we have already seen in detail. Second is, this is a improvised or improved version of stone column, which is known as geotextile encapsulated stone column. We will see in briefly. And third is use of geocomposite drain in horizontal layout or horizontal position. So first PVD we have already seen in detail. So we will see. Second we will see the geotextile encapsulated stone column. Now normally in stone column, as I told you, we make a sort of bore hole in the ground, and then progressively we fill it with stone and keep on pressing the stone. Stone spreads on the side. Sometimes when the lateral displacement is very, very high, which happens many cases when your soil is stiff clay or very, very poor type of soil, in that case, there is a huge lateral spread of the stone. Let us say if you have made this and filled with stone, even though when you give pressure also it spreads, but it does not stop there, and this spread continues sometime even afterwards also. And because of this lateral displacement of soil in lateral direction also. And in that case, the efficiency of stone column goes down. That is number one. Second thing is, even in a normal stone column also, like any pile or anything, when you apply the load, or let us say you do load test to check its behavior, up to some limit, its behavior will be ductile, and then suddenly it fails like this. If this is your load and this is settlement, after this limit suddenly, that's what happens in most of the piles also, in case of piles. So that is what we call brittle or sudden failure. That is, of course, we may not go up to that limit, but that is how, if we go up to that limit, that is its behavior. So to take care of these things, there is an improvised version of stone column where what you do is, rather than directly putting the stone in the borehole, what you do first, you make a borehole, then put these stones in a casing made out of either geotextile or geogrid or some geosynthetic material. Geotextile is most popular. Sometimes people use geogrid also, but non-woven geotextile or woven geotextile, they are the most commonly used material. So you make some stocking like that, a sort of unit, and you lower them into the borehole. So that is what is known as geotextile encapsulated stone columns. So here what happens is, when it tries to expand laterally, because as I told you, number one, because of load. Second thing, if your ground horizontal movements are significant, normal case it would have expanded, only earth would have given resistance. In this case, this hook strength of this material, the encapsulation material, this also gives it some resistance from the side. It provides lateral confinement. So that is one additional lesson. Second thing what happens is, if you are using a properly designed non-woven geotextile, it prevents entry of fine particles into the stone and prevents its fouling. So life will be very, very long. Or life means, as a column it will stand, but it will keep on giving consolidation function also for a longer period. Your pores between the stones will not get fouled by this fine grained material. So these are 2-3 major advantages of using geotextile encapsulated or geosynthetic encapsulated stone column. They are sort of used very rarely, but they are used even in India also. Some of the coastal areas, ports and other works, they have used this sort of, when soil is really very bad. So if you see their load deformation behavior, like this side is pressure and this side is settlement, this first one is ordinary stone columns. Up to here it is okay, and then I told you, it suddenly settlement starts increasing. So this is sort of point of rupture. After this, it has suddenly failed. Failure will be sudden in case your structure gets loaded to its ultimate load. Whereas when you do encapsulation with different things, with woven geotextile, with non-woven, with soft grade 1 and 2, you can see more is the restraining strength provided by this geosynthetic here. This restraining strength. Number one, it becomes more ductile and it takes more load. You can see here failure. There is no sudden or abrupt point of failure. It is a ductile failure, like your any ductile material like steel or whatever sort of ductile material you see. So that is the advantage of using geosynthetic encapsulated stone column. As I told you, nowadays, this is a recent development, maybe last 7-8 years or something. They become popular. Before that, and third type use of geosynthetic is use of geocomposite drain. Now, of course, we'll see what is geocomposite tomorrow onwards when we go to geosynthetic. But just to tell you, basically, this geocomposite layer consists of, there is a material or there is an element which is known as geonet in the middle, and on both sides of it there are non-woven geotextile layer, and both this combined thickness will be maybe 10 to 15 mm, not more. Very thin element. This element has got very, very large discharge capacity. In fact, just to give you an idea, if you take 1 meter thick sand layer, good sand layer which is 1 meter thick, and replace it just with this element, and if you calculate its discharge capacity, purely discharge capacity from Darcy's flow law, you will find the factor of safety is somewhere around minimum 10 to 15. It means 15 times more flow this can carry than this. Second thing, because of this geotextile and all, the fine particle of soil will not enter here and spoil its discharge capacity over a long period of time. We'll see it in detail when we go to geosynthesis. So this is how this sort of material where two geosynthetic products are merged together. Here, geonet and non-woven geotextile, there are two products. They are known as geocomposite. As the name suggests, it is a composite. So more than two materials are joined and used. So these geocomposites can be used for many purposes. We'll again see tomorrow. But one of the purposes for ground improvement. How? Normally, whenever we are constructing a bank, and let us say this soil is fine grained, very, very fine grained. Whether it is weak and all, we are not seeing for the time. It's very fine grained, and the naturally available material in that area also is very fine grained. This happens especially near your river courses and all those areas where sand and all will be very fine. Though it is not unsuitable, as it is not fully unsuitable for not to be used as bank, but it is very fine grained. It's got its own problem. And so this material also is very, very fine grained, your subgrade as well as subsoil. And problem becomes more when your water table also is very high. So in these cases, what will happen is, even if we don't talk about consolidation and all here, at least this water will rise to this, and because of fine grained material, significant pore pressure may get built up in these banks, and which may endanger the safety of the bank itself. In fact, there have been a few cases in railways where the banks in service have failed. Normally, it is very under these conditions. And to avoid this, the best thing which is done to avoid this is this: whenever banks are designed in such area, people what they do is, at the base of the embankment, that is at junction of or at the natural ground level, here people put a sand layer. Half of it goes below ground and half of it goes above ground, and of course its thickness varies from place to place, but about 1 meter. Normally people they put 1 meter thick sand layer. Now what is the advantage? Number one, whatever water is coming on top, it will get discharged on the side, so your buildup of pore water pressure will be avoided in your bank, so it takes care of your bank safety. Second thing, sand is a good bearing material, so this load coming from the top gets reduced while getting transferred. So it acts as a stress reducer also before it goes to ground. So even if this is fine grained material and its bearing capacity is under question mark, it guards against that, and it gives good uniform distribution of load at junction of embankment and subsoil. So this is a sort of standard practice. Like you go to eastern part, this area, Farakka, Sahibganj, and all this area, if you see most of the banks where either people they themselves have designed or RDSO has given some consultancy. Many other areas, this sort of design is very common. Nowadays, problem is that availability of sand is very difficult. Getting good sand at 1 meter thick, either it is very costly or due to environmental restrictions, you don't get the sand. So as a replacement of this, it is not as a ground improvement per se, but as a replacement, this was a ground improvement measure. As a replacement of this, what you can do is, rather than 1 meter sand, you can just put 75 mm thick sand only at bottom and 75 mm thick sand at top. So total 150 mm, and here you can put this geocomposite drain at this place. Now with this, number one, as I told you, its draining capacity. We did 2-3 such designs in RDS, I remember 2-3 years back, and we calculated with flow net and all, its drainage capacity is 14-15 times more. It has got longer life than sand because the sand over a period of time will get fouled with this fine grained soil, whereas this geocomposite does not get fouled so easily. Then this geonet plus this, it gives you some reinforcing, even though it is not designed, but as a byproduct, it gives you, it acts as a reinforcement there also. It increases the strength of your embankment also. So this is the use of horizontal geocomposite drain. So same thing is written here in case of fine grained subsoil as well as subgrade with water table also at high level. It is a good practice to provide a separator cum drainage layer. This sand layer is a separator cum drainage layer of sand about 1 meter thick at the ground level. The thickness may vary a little bit here and there depending on height of the bank and what type of soil it is, roughly 1 meter. Now, this is one. So, wherever there is a scarcity and you want to reduce the thickness of sand, you can do this by laying a geocomposite drain layer, which is sandwiched between two layers of sand of about 75 mm. So, this is one layer of sand of 75 mm, this is another layer, this is sand layers, and then you can put this geocomposite in between. Very simple. And then your pore water pressure here will almost remain zero. With that, you can take lesser RU value, and with lesser RU value, your bank slope need not be very flat. A lot of advantages you get out of this. So, this is actually a replacement of sand wherever you are having problem in getting sand or sand is very costly. And RDSO has issued it's a specification also for this geocomposite drain. Last year, they issued a specification for this. This is the specification for this geocomposite. Now, we have seen various methods of ground improvement, how they function, what are their advantages and disadvantages. Next thing I want to tell you, a few 1 or 2 slides, is about what aspects you must take care when you give consultancy. Because this again, based on my personal experience, I've seen most of the time wherever we have to get some ground improvement system design, we give a consultancy. Now, whenever we take any technical advice from anybody, it may be legal advice, it may be medical advice, it may be engineering advice, we must always remember one thing. Quality of advice depends to a large extent on quality of question asked. If I have not framed, number one, my requirement in proper way, if I have not asked proper question to a legal person, or if I am not able to explain to doctor what is my proper problem, you can be very sure that you will never get a proper advice. Same happens for engineering consultancy also. Of course, sometimes even after expressing your problem properly, if your consultant is incompetent, you may not get good advice. But one thing is sure that if you yourself are not very clear in framing your terms of reference, then you will never get good advice. That is for sure. So that is number one. That whenever we give something to consultancy, I must know that what do I want from the consultant, how I want it, what are my terms of reference, what are my boundary conditions. All those things have to be explained properly to the consultant. It is not that we just tell the consultant, I want to do some construction here, you give me some methodology. Then he will give some methodology, we will do something, and something will happen. This way, consultancies are of no use. That is first stage when we give work to them. Second stage is after we receive the deliverables from the consultant, maybe consultancy report or design, we must always go through it and see that it contains all the necessary things which we wanted. Many times I'm telling you, I have been witness to this. Why I'm telling you this? This is the slide which I want to highlight to you. Number one is, as I told you, proper problem presentation to the consultant and what is your requirement. This is very, very necessary. Very necessary. You have to tell what you want, for what purpose you want, what is your boundary line. Let us say you go to doctor, you have to tell, and few of the things which you must be very clear. Number one, you must always tell them what is your required factor of safety. I found our consultants are highly ignorant because most of the time they are working in NHAI, there the values of factor of safety are a little bit different than our values. And many reports, not one I've seen, they quote the references because they are more conversant with NHAI, they have done more work. They write factor of safety as 1.32, which is the requirement in NHAI, not in our cases. We don't have no figure as 1.32. So like 1.2 is our short term or end of construction requirement, and 144 is long term. And if bank is less than 4 meters, then it is 1.6. Similarly, I am yet to see a report in case of doubling. Whenever you give any consultancy for doubling new line construction, I'm talking about ground improvement in this case. And as I told you by an example yesterday, if anything happens to your bank, new bank, 100% it will affect existing bank also. Now, new bank is section under doubling, no train is running, so you can strip it open, you can rip it apart, and repair it. On open line, trains are running, and most of the time it does not get repaired, and it becomes a source of permanent speed restriction. So, whenever I'm designing a ground improvement system, my consultant and me, I should be aware of the fact that there is an existing bank standing there. What are its properties? What are its dimensions? How your work will affect that bank? And we must give this to consultant with dimensions and material property. If it's not there, then either include it in his scope of work that he will take samples there and check it, or you get it done separately and give it. Most of the time, this is missed. And with that, what happens is we do new work construction and create problem for open line person who has already got a number of problems in addition to this. So this is another thing. This is a very, very relevant fact at the site. When you will be doing work, you will be getting some part of that bank also. Some of your bank lateral pressure will get transferred to that bank. It must be factored into our design. Second thing. This is just few things, but there can be many such things. Whatever is your site, whatever problems, whatever issues are there, everything we must write there. Second thing is, once report comes, as I told you, you must study the consultant's recommendation before you go to field for implementation and check, as I told you, explicitly about stage construction. If stage construction is there, is it defined? What is stage height? What is the waiting period? Instrumentation? It should all be defined in your report. Otherwise, it is incomplete report, unimplementable. You should not try to. You must try to consultant, please give a proper report. This is half-cooked report. Similarly, another thing I told you earlier, your ground improvement measure, whatever type of it may be PVD or it may be stone column or it may be on R&R, it should not stop at the toe of the bank. That is not line of actual control between India and China. Your pore water pressure and other parameters don't stop at that place. Their effect continues something outside toe of your bank also, and they must extend beyond toe of embankment also. And if you read literature normally, people, of course, depends on type of soil and type of bank and all, but thumb rule is h by 2 to h by 3. So try to go from h by 3 to h by 2. Your bank height, 1/3 or half of that, you must extend your ground improvement measure outside the toe of bank also. It should not stop at the toe of bank itself. And in case of poor soil, I told you previously also, again repeat, there should be no pond or ditch within h plus 3 meter beyond toe of embankment. And if you are having, then fill it up with whatever cheapest type of soil, locally available material available there. Idea is water should not be allowed to stagnate in near vicinity of my bank. Otherwise, in case of weak soil, already we are having problem. And if water stagnates there, finally it will percolate or through capillary action, it will rise above and it will be a lot of problem. So these are the few things, just few things. This is not the end of it. This is not an all-inclusive thing. These things should be always taken care of whenever we are giving some work to consultant. So not leave everything to consultant. Okay. Now, probably we are coming towards the last part of it. I have told you that whenever we do stage construction or any ground improvement, even though we do theoretical calculation, which we'll see just after this today, but these theoretical calculations I will show you there also are with a lot of assumptions, lot of things. In field, things don't go exactly like this. So the proof of the pudding is in eating, not in preparing. So we always do instrumentation and monitoring and observe the things at site, and based on those observations, our further decisions are taken. Not purely on base of theoretical calculations. So what sort of instrumentation and monitoring are required? What are the parameters to be monitored? We will see. So design of embankment is done with available field and lab data also. Now we may be taking sample at once in 200 meter or 250 meter or 300 meter. Even though there is no major change, but still there are changes within 200 meters. Soil does not remain exactly same. That is the one reason why calculation data is not exactly matching with field observation. And the prediction of response of embankment and subsoil is based on design assumption and soil parameter. We make some design assumption that Terzaghi's theory is valid or Casagrande theory is valid and all. All right, to a large extent it is valid, but it cannot be 100% valid or 100% straight in the world. There will always be some deviation. And the soil parameters also we have done one lab test of maybe for 200 meter. 200 meter it is not effective made product like steel or something that it will remain same. Even there also it does not remain same. There is standard deviation. So in case of soil, your soil is non-homogeneous. A lot of other things. It has got history. It has got stress history. So many things. And therefore there are always variations from what we conclude theoretically. And therefore these theoretical things cannot be 100% accurate. They are good guide. They are to be used as a guide for further response, but they should not be reliable. And therefore, monitoring of critical parameters like pore water pressure and settlement, these two are most critical parameters. There are some or two other we'll see, but pore water pressure and settlement, these two parameters are most important parameters in case of ground improvement. So these two are generally invariably monitored. Second thing, the comparison of predicted and actual performance during construction and taking corrective action well in time. So once let us say I'm doing a construction site of 100 km and I first predict something, then I measure it and then I say this much is deviation. It gives me a guidance also for further work. Further I will get a range. Maybe I've done first 10 km, with that I will know that in next stretch how much is the deviation likely to exceed, how much is deviation likely to happen. And based on observational result, it also tells me to take corrective action well in time rather than being purely guided by my or 6 years to 5 months. This is the difference by faster consolidation. Here they have plotted predicted versus actual settlement also. This is of course for theoretical purpose. This is in number of days and at a particular location. Now even this also, whenever you have this drainage through this vertical drains, one is vertical drainage like this. In addition to this, there is radial drainage also. So in calculation, what they are trying to show is radial drainage is also important and it has got a significant effect. So if you take only vertical drainage, then your degree of consolidation, this side, the chart would have been like this, theoretical, okay, without PVD or something, normal. Then PVD for combined radial and vertical drainage. Now there is a coefficient of consolidation, and coefficient of consolidation in vertical direction is CV, in horizontal direction CH. Normally your CH is more than CV, but for that you have to do a directional permeability test, which is difficult. So many times for the sake of simplicity, you assume CH equal to CV. So if you assume CH equal to CV, then this will be your predicted degree of consolidation. And if you assume CH equal to 3 times CV, then this is your predicted degree of consolidation chart, and this firm line is actual chart. So what they are trying to say is that if you can do permeability test, directional permeability test for horizontal direction, in that case, and if your CH is more than CV, you can take advantage of this time also. Otherwise, in normal case, I would have assumed, let us say I have to get 70% consolidation. Draw a line here. By my normal calculation, I would have taken 160 days. Actually, it is 60 days only. In 60 days, I'm getting this much, provided that I have data of CH also. We will see in our calculations. We have got different parameters CH and CV. If you have got values of both, you can take advantage of that CH also. Otherwise, you will be on safer side only, but you will be giving more time than what is required. So this is about this side. Second case history is about there is a station yard by name Udaipur in NF Railway in Tripura. This is after Agartala, new line after Agartala. Agartala was conversion, the new line extension from Agartala towards Sabrum, I think. Agartala Sabrum, yeah. So there is a major station there, Udaipur station yard. This is second case history. In this, the height of embankment, the design height is 6.2 meter. And they started embankment construction in 2010 without any ground improvement. First, no ground improvement was planned. So like normal embankment, we started building the embankment. 6.2 meter height. Please remember these figures. Then, when the embankment height reached around 3.5 meter, number of failures started. The bank started sleeping. There were base failures, and for nearly 1 year, September 11 to December 12, they were not able to construct the bank. They used to repair, construct, again fail, repair, construct, fail, and there used to be base failure with heaving going up to 30 meter distance from top of bank. As I was telling you, normally this heaving occurs far away from the bank, where the slip circle may be striking your normal ground level. So there was heaving, classical case of shear strength failure, base failure. Then when problem became severe, they gave a consultancy to IIT Guwahati for detailed geotechnical and hydrological investigation. And I don't know, it must have been known, but later on it was confirmed that where the bank is being constructed is actually a lake. And lake bottoms and all this water bodies bottom will have stiff clay or clay, very poor type of clay. And water level during monsoon goes up to 3 to 4 meter above the existing ground level. So 6 meters is your bank height. Water level will cover 3-4 meter of that. And before going to water level at 3-4 meter, only all your failures have started taking place. And the depth of soft clay is 9 to 13 meter below existing ground level, quite significant depth. So what they did, they took consultancy from IIT Guwahati, and what they suggested, first of course, whenever there is a bank which has failed, first thing which is done is strip away everything whatever you have done, bring it back to wherever existing ground level was there, then do ground improvement and reconstruct the bank everywhere. That is the methodology. It is not that half slip bank is constructed again and something. We should not attempt that also. So strip the embankment, construct it, and rebuild it after proper ground improvement measures. And they evaluated various methods, PVD, stone column, and all, and finally they found that PVD will be suitable. Normally this is the sequence. First you evaluate PVD. If PVD is also not working, then you go to stone column. That is final thing. Because stone column makes it very strong, but they are very costly, very costly. So if PVD works, then we must always go for PVD or vertical drain. And this is the details of PVD. They provided PVD in triangular pattern. Spacing was 0.8 meter center to center. Then over ground, first 150 mm porous sand layer, right? With top of PVD in this layer. So first 150 mm porous sand layer. Over this, a layer of non-woven geotextile. Over that, again a 300 mm thick layer of porous granular material, and then a woven geotextile. So over ground, effectively around, you can see around 0.5 meter depth of sand, 150 plus 300, and one layer of non-woven and one of woven. Why woven and non-woven? Of course, we'll see when we go into geosynthetics. Woven geotextile gives you good shear strength, and non-woven geotextile is a good drainage element. It helps you in drainage. So that's why they have put one layer of that. Then stage construction. The bank, they said you must construct in stages with sufficient time between each stage. Of course, the stage time, as I told you, first we calculate theoretically, but we never go purely by those calculations only. You measure the settlements. So monitoring of settlements using plate type settlement gauges and pore water pressure with Casagrande type piezometer. So there are settlement gauges, piezometers are used, and Casagrande type piezometer are most commonly used piezometer. They measure the pore water pressure, and when they confirm you that your required degree of consolidation for which you have designed your stages, which can be 70 to 90%. Normally, as I told you, nobody works in less than 70% degree of consolidation, and normally maximum you try to get 90% before constructing next stage. So that confirmation is by actual observations and not merely by theoretical calculations. And here, of course, they took 95% consolidation in the typification of design, and it took around 100 days. And you can see total settlement was 1242. In 6 point something 2 meter bank, settlement is 1242, 16215. This was I have been telling previously also. The settlement in these soils is very significant. It is not a small amount of settlement. This is how it was. You can see here, this is the existing ground level. These are the PVDs. They are in triangular pattern at 0.8 meter center to center. This is your drainage blanket. In this drainage blanket, first 150 mm sand, then this is 150 mm porous sand, then non-woven geotextile, then 300 mm another not sand but free draining soil, and then woven geotextile on the top as base for here. And on this is a normal bank, and say 2:1 they are able to construct and make it safe. Otherwise, it will be very flat. So this is what was done, and this is soft clay layer. I told you 9 to 13 meter, and then of course proper berms wherever needed. So you put some settlement gauges here also, and so that you measure is there any settlement, and mostly here. So this is about settlement gauge. This is a typical instrumentation scheme, not very complicated, very simple, which you can follow. And this is only a guideline. If your soil is varying drastically, maybe you can reduce the spacing. If soil is more or less same, high banks are less, then maybe you can put less number of equipments. Also, this is a typical instrumentation scheme. And then once you put the instrument, at what frequency you should monitor it. First is when your work is going on, when earth filling is in progress. So when work is going on, your frequency is daily in the area where work is going on. Now, work may not be going on continuously everywhere, even though you might have put instrument for a length, but work may be going on in a patch. Let us say this is your total length, and even though you put instruments here, but your work is going on this stretch only. So now there are two categories. One, work is going on, but exactly their work is going on. Second thing, this stretch where nearby work is going on. So wherever actual work is going on, there daily we must take their reading. And other adjacent locations, even once in a week, is sufficient. Because there will be some disturbance, some effect may be there, but it will not be as pronounced as location where work is going on. So there it can be once in a week. And once your work is completed, means you have reached the desired fill height, whatever was your fill height. If you have reached that height, then once in fortnight is sufficient. Every 15 days, you and normally as I told you, you take two readings very frequently, settlement and piezometer reading for water pressure. And wherever horizontal spread is noticed or expected, you take reading of horizontal increment. That's all. Only 3 readings. Nothing much. It's a very simple exercise. You can train even in class also. You can go and take the reading. Only thing is those readings must be seen by a technically competent person and interpreted that what those readings are speaking. It is like our BPO temperature record. That recording can be done by anybody, but what is it indicating finally? Whether you are getting well or you are further getting unwell, that is interpretation of results. Okay, and this is the last thing. There is a thing called sandwich construction. Now, there is a technique called sandwich construction. Probably I use this word in slope stability analysis also while we were talking about RU value, and I told you sandwich construction, we take RU equal to 0. When do we go for sandwich construction? First of all, when we find that there is soft clay in subsoil as well as fill material. In fill material also CL, ML type, CIMI type of soil is allowed. It is not prevented. So if soft clay is there, let us say in subsoil, then many times we go to sandwich construction. And what is sandwich construction? This is sandwich construction. This is my ground level. So as I told you, always at the junction of embankment and subsoil, we give a drainage blanket. So this is a sand layer, and normally it is given 1 in 20 or 1 in 30 slope, so that water gets drained out. Sometimes people use for full width, sometimes they use half of the width also. That also is considered sufficient. This is first layer. Then you build your bank with normal thing. Then in between you will intercept with this sandwich of sand. There are sand layers. There are sand layers in between 20 to 30 centimeter thick. At this is 20 to 30 centimeter sand layer at every 2 to 3 meter height. And here, when your bank height is only up to 6 meter, then your slope given is it should not be flatter than 2:1 as we normally do, and no. This thing is required, what you call berm. But the moment bank height becomes more than 6 meter, then we must give a berm. And berm minimum 1.5 meter minimum. But normally, whenever you give a berm, 2-3 considerations we always give. Number one, if this is my bank, from here water will come. So you will provide a drain here. That is first thing, to drain out this water. And then this will be used for movement of your vehicles and also for maintenance and other purposes. So considering that, you must give the width. And normally, you should not give less than at least 2.5 meter or so, depending on what sort of vehicle. But normally people give 2.5 to 3 meter. So 1.5 of course is given minimum here. And below this, after 6 meter, whatever further your bank is there, the minimum slope given is 2.3 horizontal is to 1 vertical. In case of sandwich construction only, not other thing. Advantage of sandwich construction is in case of sandwich construction, your RU will be always 0. So you can refine this also later on. This of course not. With RU equal to 0, you can see whether you can make it a little bit steep also by doing slope stability analysis. This is the general scheme of sandwich construction. And normally we follow sandwich construction. This is what is given the requirement. When soil, the fill soil has got fill soil, not subsoil, has got permeability less than 10 to the power minus 2 centimeter per second. It means it's very fine grain with very less permeability, and chances of poor water pressure building up there is more. And as I told you, provide 20 to 30 centimeter sand layer at every 2 to 3 meter height, and wherever height of embankment is more than 6 meter, provide a berm. And this berm acts as subbanks and it increases stability. This already seen. It also acts as a pathway for maintenance. And provide 1:20 cross slope in the sand layer. It is not a horizontal sand layer. It has got a cross slope 1:20, so that water gets drained out.